Hey everyone. This lecture is sort of a mixed bag. We're going to finish off queuing systems with two more systems, both of which have infinite capacity and maybe are a little more applicable to scenarios than the models we've looked at so far. And then we're going to start off on our last topic of the class. This topic is called hidden Markov models. It's the newest tool of the various different things that we've looked at in this class, and I think you'll enjoy it. The idea behind these is that there are two processes that you think might be linked, one of which is not easily observed, or maybe not even possible to observe, like, for example, some sort of emotion or mood, or maybe some sort of like physical phenomenon that you don't yet know about, so it's not easy or even maybe possible to make a direct measurement of. If you think such a process exists and that it's Markovian and that it's linked to some other stochastic process which is directly measurable, then there are ways to kind of learn about the system and learn about the underlying hidden process. All right, let's go. So we're going to look at two queuing systems today, our last two, and both of them are going to have infinite capacity. The first one is going to be MMS. So the capacity is infinite, but we constrain the number of servers. And the method for working out their stationary distributions is going to be pretty much the same as the previous ones, but we'll sort of think about how do you enforce these model restrictions and what are the consequences. So just as a reminder, the naming system means that the arrivals are a Poisson process, and the waiting times are exponentially distributed. And both of these we're going to enforce the kind of model restriction, the model constraints by using parameters lambda sub n, where the n is the label of the state, and mu sub n. And so for the state, of course, the states are of course still going to just be, you can have any number of customers, any non-negative number of customers, so 0, 1, 2, and so on in the system. And since it's infinite, that can just be any number. Okay, and so we've got S servers, and we have infinite capacity. And the fact that there's an infinite capacity means that there are lots of ways that there could be no stationary distribution. It could be that the system, what we call, blows up, right, where the distribution of the stationary distribution just sort of drifts off, so that you just have it never stops changing over time. All right, and so we're going to use the same kind of model before. So we're going to have birth and death process. And in order to have this thing work the way it's advertised, we're going to have lambda n is the same for all n. So that lambda here is just a constant. And mu sub n, this one is a little different. This one is going to be, we want to have one mu per occupied server. So maybe we'll write out the expression for it first. And then just you can kind of describe it that way. And so for this one, we have the following. So you can actually write it in a shorthand notation. So it's the smaller of n at s, and then times mu. And so this looks like the following. So it's mu times n if n is less than s. But once the number of people exceeds the number of servers, then you can't have any more people being served, and so then it's s times mu. if n is greater than or equal to s. Okay, and so that's the strategy here is one factor of mu for each occupied server. Or each server that is in doing work, processing a customer. So this one, we're just going to make a claim about what the result is for the stationary distribution, and we're not going to prove it. I'm going to leave that to you as an exercise. You'll see this in the tutorials. All right, so the proposition for the stationary distribution for this system looks like this. So we say, oops. So we say for an MMSQ as above, with the parameters mu and lambda as described above, then there's only an equilibrium distribution. Just so, as I was saying, it's not always the case that there is an equilibrium distribution. So you have equilibrium distribution or stationary distribution if lambda over mu times s is less than 1. All right. Another way to write that using our notation that we've been using already, where we have or if r over s is less than 1, where r is equal to lambda over mu. That's just resurrecting that notation that we used in the last lecture. Okay, but if that is the case, if you do have a stationary distribution, so in that case, you have the following. So we're going to write down pi n and pi 0 separately. Pi 0 is kind of a special case. So pi n looks like this. So it's it has sort of two versions depending on whether or not n is bigger or smaller than s. So if it's smaller than s, it looks like this. So it's r to the n over n factorial times pi 0. So this is sort of maybe to be expected for n less than or equal to s. And of course bigger than 0. There's no meaning to n less than 0. And if n is bigger than s, then it just looks like this. So it's s to the s over s factorial times r over s to the n times pi 0 for n greater than s. I guess you could say greater than or equal to, they're the same. Okay, so that's what pi n looks like. And then pi 0 itself, which sort of governs all these things, because each component is multiplied by this. So pi 0, this guy is equal to, has two terms, two different sums. So a sum j equals 0 up to s minus 1 of r to the j over j factorial plus s to the s over s factorial, the sum of n equals s to infinity r over s to the n and all this to the minus 1. So like I say, we're not going to prove this here, but I'll leave that to you as an exercise. But that's the result. So for our last Q, we're going to take a version of what we just did, except we're going to let the number of servers become infinite. So I'm just going to steal this, bring it down, and reuse it again. Just change it up. So we've got the same setup, except that we're going to have infinite servers. And this thing, maybe you should kind of ask yourself, like, what exactly does this correspond to? I think you can sort of imagine this as like, I mean, we've probably all used this kind of thing where maybe there's some sort of like artificial intelligence handling chat complaint system or something like that. So maybe that's what's happening there. So an AI call center. It's certainly conceivable to have infinite capacity using something like that, but the infinite servers is a little tricky. So maybe this is how you could do it. So I don't know. Put that as a question mark. Maybe that's what's going on here. All right, and so it's going to be a birth and death process again, but there's no restrictions. So we're going to say lambda n is equal to lambda for all n, and mu sub n is equal to mu times n. So it's the same strategy for mu, except that there's no restriction. You don't have to shut off the counting up of the servers that are processing customers. All right, and so we'll just say what is the result again. So proposition. So for the m infinity q, change this back to blue. There's always going to be equilibrium. So equilibrium always exists. And that sort of makes sense. Sorta. You're never going to blow up in the sense that there's always servers ready to process anyone who arrives. So there is always an equilibrium in this case. And pi sub n looks like this. So it's r to the n. This might look familiar to you. E to the minus r over n factorial. All right, you should recognize that. Maybe. So here, just as a reminder, r is, lambda over mu. So that means that x is Poisson, a Poisson process, or sorry, it's Poisson distributed. So the limit as t goes to infinity of x, it's Poisson with parameter r. The proof for this, it works just like all the others that we've seen. So we're just going to borrow from the all-powerful proposition from the birth and death process section of the notes, or of the lectures. So this is from proposition in birth and death process. Oops. Lecture. And I think in your notes it's 5.4, proposition 5.4, I believe. So this is the thing we've used over and over again now. It says that pi 0 has the form 1 plus capital R all to the minus 1. And I'll define capital R in the same way. So capital R is a sum over n equals 1 to infinity of capital R sub n, where capital R sub n has this form that we've been using. All right, move these guys down. It's this ratio, and up on the top there's all the lambdas, so we have lambda n minus 1, n minus 2, and so on. Sorry, these are multiplying each other all the way down to lambda 0. And then in the denominator, product of a bunch of mu's, so mu, and starting with n and going to mu sub 1. All right, the same notation that we've been using. Right, and now in our case, so here, all the lambdas are, any lambda sub n is just lambda, so that numerator is lambda to the n. And the denominator, that's how many there are there. And the denominator, each of the mu's is n times mu. And so this gives us n factorial times mu to the n, right? Or you can rewrite this as r to the n, little r, over n factorial. Okay, and then it's straightforward just to go ahead and work out what are the different things. So pi 0 then, right, so it's 1 plus this sum, n equals 1 to infinity of r to the n over n factorial. And you could, and that's all to the minus 1. You could just make that a sum starting from 0, right? And the first term is 1, and so this is sum over n equals 0 to infinity of r to the n over n factorial to the minus 1. And that's just the Taylor series for e to the r, e to the minus r, or e to the r 1 over that. Okay, so that's pi 0. And then pi n, so I'll just do it over here because it's so fast. So pi n, right, it's big R sub n times pi 0. And so that's r to the n over n factorial e to the minus r, as promised. All right, so that's the last queuing system that we're going to look at. So we're now going to start off on our final topic of the class, and this is called hidden Markov models. We're going to spend the rest of this lecture on just sort of giving a small overview or introduction of what this topic is. And then the next lectures, the next two, our remaining 2 lectures, we're going to work through a bunch of examples and see some important results. So hidden Markov models, these are a newer tool than most of the ones we've seen so far. So let me just give you sort of an overview of the topic here. So this is newer than our other tools or our other topics. And I'm going to show you, I'm going to sort of demonstrate that with a little bit of a small plot. It's the most recently developed. I think that its origins were in Russia in the 50s. In the 1950s. But as you'll see in this plot I want to show you, it doesn't seem to have taken off internationally, at least not in the English language, until later than that. So let me go grab this thing I'm talking about. So I'm just going to paste in this picture that I got from using Google's Ngram website. I don't know if you've ever used this before, but it's kind of fun. I'm not a very good historian, but I still think this is kind of a reasonable thing to kind of look at. So this is just a plot of the use of, or relative use of words. I think in this case it's relative to today. In some whole zoo of books that I guess all the books that Google knows about or something like this. I'm not exactly sure what is the database that this is based on, but it's meant to be some sort of representative collection of books in the English language, I believe. And what you see here is, so here's a list of all the topics that we've covered, or some representative of them. So Markov is there, random walks, branching processes, and so on. And the one that we're and almost all of them sort of take off here in the 50s, and then level out to whatever the amount of use they are today. But hidden Markov models are this light blue thing, and they don't really take off here until like the 80s, and they jump up pretty quickly. And I just thought I would point it out that they sort of jump up at the same time as neural networks, which we're not using in this class, but it's just sort of an indication of how kind of new the topic is. So I think it was initially developed in the 50s, but it doesn't show up on this plot just yet. There, I believe it was used for signal processing and speech recognition in the 70s, and so that might have been what started its rise. Over here is like a small bump right here, and then it got used in other contexts. But yeah, I just thought that plot is kind of useful for getting an impression of how this topic is newer than the ones that we've been seeing so far. And so here, I just want to start off with just like a sort of a rough description of hidden Markov models. All right, so the idea behind these things is that there are two processes that you're interested in, one that's easy to observe and one that isn't. And so we're going to say that you have an observed process, and we're just going to require it to be a stochastic process. Oh, we'll make another requirement as well. Hang on. So this is an observed stochastic process. So we'll say that the time is discrete. So x sub t such that t, and we're going to change conventions slightly here. We're going to suppose that it starts at 1. And sometimes it's the case that x is actually a continuous variable. We'll see one example of that in our sketch overview today. So sometimes, maybe even often, continuous. But the time parameter is discrete here. You could probably generate a discrete, maybe using a discrete stochastic process from a continuous one. Well, we'll think about that in a second. But in any case, for us, it's going to be the case that time is discrete. The stochastic process itself can be continuous if you want. So the state space is what I'm referring to there. And so each x sub t has some dependence, or depends on some unobserved other process. Some unobserved Markov chain. All right, so that's another stochastic process, and we're going to label this guy with capital S, so not to be confused with state space, hopefully. But I'm just following the notation that you might find in books, maybe. And so this is S sub t, such that t is 1, and so on. 1, 2, and so on. Right, and so this thing is sometimes called the parameter process. but I like to think of it as the unobserved process. And this is a Markov chain with its own finite state space. Discrete. State space. Okay, and so other names that you're going to encounter for these, so these guys, S sub 1, S sub 2, and so on, these guys are referred to as the states. Right, so they're the different time measurements of the hidden Markov chain. Those get referred to as the states. And then the process, x sub t, this gets referred to as the state-dependent process. Right, so this is just some terminology that you're going to encounter. And let's try to think of two different examples here. One where the state-dependent process is discrete, and one where it is continuous. So we're going to look at a couple of examples, as I said, but I think I want to emphasize first what are our sort of requirements. Right, so when we work on these examples, here's the idea. We want to make sure of two essential ingredients. All right, so one, we want to require that it's reasonable to suppose that the measured process, x sub t, depends on the unmeasured thing. Right, so that's key ingredient number one, that it's reasonable to think that these two processes are somehow linked together. And two, that it's reasonable to suppose that the unmeasured thing is actually a Markov chain. Oops, reasonable. And the best thing about these two requirements is that you can just say that anything's reasonable. Sometimes the best justification that something is reasonable is that you supposed it, and then it turned out things worked out. Okay, so we're going to first we're going to do a discrete example. All right, so example number one. And this one, I'm going to deviate from the notes a little bit, just slightly. Let's suppose that we're interested in students. All right, so we have students or a student. Let's say you're watching or monitoring a student. And let's suppose that they have various different things that we can sort of either measure or not. And let's suppose, so the thing we measure, x sub t, let's suppose that this is a measure of whether or not the student is studying. So we'll say it's 1 if studying, and 0 if not studying. In principle, that's measurable. You can say, well, were they reading a book? Were they working on a problem set or a problem or an exam or in a lecture or something like that? In principle, this is measurable, whether or not a student is studying. And then let's suppose that there's this other process, S sub t, that's not as easy to measure. And we could use 1 and 0. I'll use what you see in the notes as well. So we'll use 1 for being, I want to say like intellectually curious or something like that, but I guess I'll just say thoughtful. Something that's sort of ambiguous and a little bit hard to measure. And then we'll say 2. There's no reason to call this 2, really. I'm just sort of following what you might encounter in your notes, so it might help you a little bit. We could call it 0 if you want. Maybe it doesn't have to be thoughtful. Maybe it could be some other state. So I was going to say not thoughtful, but maybe we could say, we could suppose there's only 2 different states here. Thoughtful, and I don't know, sleepy. I mean, that's not, sleepy is not something that's super easy to measure. Maybe you could, I don't know, with heart rate or something like that. Not sleeping, but sleepy. So these are the 2 different states that are a little hard to measure. So x sub t, this is measurable or measured. And this one is not, or not observed. And you can collect data for this in principle. So maybe you can only collect data for the 1. So you got like x sub t. You have this whole collection of these guys. Well, let's see. How do I want to write this? I guess I could write it as a vector. But I'll follow what you're going to encounter in your notes. So we'll say like x1, x2, x3, and so on. And let's just say, so you've got like, maybe these are measured once per hour or once per day or once per year. I don't know. And so let's just say these are like 0, 0, 1, and so on. So you have this big collection of whether or not the student was studying. And then in principle, there's also this other measurement here, or not measured, sorry, this somehow maybe hidden record of the state, S1, S2, and so on. And this one, so we'll say it's like thoughtful, sleepy, and so on. Now, I don't know if this is a great model. Is it a good idea to say that studying or not studying, is it reasonable to say that those are linked to whether or not a student is thoughtful or sleepy? I think that seems reasonable. And is it reasonable to think that whether or not they're thoughtful or sleepy is a Markov chain? Maybe not. But we could certainly go with it and see what happens and see if you get somewhere with it. Maybe, the probability that you're thoughtful depends only on whether or not you were thoughtful at the last measure of time. That's the idea. We could certainly try this example. And so we're not going to work this out. This is just a sketch, right, of what kind of things you might encounter. All right, so let's finish off with just an example that's a little bit different, that's sort of continuous. So we'll make this guy another example. And let's suppose we're interested in a customer in a store or in a shop. And let's say it's a super modern shop, or I don't know if it's super modern. Let's just say it's a modern shop. It has an app, and when you're in the shop, it actually measures your position regularly, like every few seconds or something like that. Or maybe there's cameras. You don't have to have an app. You just watch people, and cameras monitor where people are. And so let's suppose the shop looks kind of like this. So I'll make like a map of the shop. So let's say over in the front here, so let's like make it like a grocery store. So there's like fruit over here. And then, I don't know, let's say over here there's like meat. And then maybe another aisle over here, some like dairy. Next aisle over here, let's say crisps or chips in my country. So let's say this is the picture of the store, and shrink that down a little bit. And I don't know, let's put some others though. So like candy. And then maybe over in the back over here, there's like drink, alcohol, or something like that. Anyways, let's suppose that's what the model of the store looks like. And here, let's make this look all pro. There we go. And let's suppose you've watched a customer in the store. And let's see, so how am I going to draw the customer? Let's make them brown with a little bit bigger dot. And you just monitor their position when they're in the store. And so let's say they come in and there's the customer at one moment of time. And then here's the customer at another moment of time. And here's the customer at another moment of time. And then the next moment of time, they're over here. And the next moment, they're over here. And the next moment, they're over here. And then here, 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 here. And then the next moment, they're here. Then here, 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 here. And then suddenly they're over here. Maybe they just have a stop over here. And then like kind of going along like this. Maybe they forgot something. Just wandering around here. Tying their shoe, I don't know, all kinds of stuff like this. All right, so this is the customer location at regular intervals of time. And the idea, maybe you'd be interested in this as the shop owner or something, is to wonder, are they consuming or are they just wandering about? And so that's your sort of like your hidden state here. So we'll say S. How do I want to? I'm going to use blue again. So we'll say S. Oops! Whoa! I got the big pen. All right. So let's say S. T has these two possible states: consuming or just wandering. Right, and I guess you could label those with numbers or something like that. But let's just suppose we use those words here. Maybe we give them colors. So let's say consuming, we'll go with Christmas theme. Consuming is green. Is that too green? What do we got? Other greens here? It's too hard to read against this. Let's go with this dark thing. And then wandering, we'll call this red. Maybe the shop owner doesn't want wandering, they want consuming. Yeah, traffic light system. There we go. And so maybe you look at this and you think, well, okay, I think over here this is probably consuming, and this is probably consuming here. But maybe not. I don't know. Who knows what's happening here? Maybe they met their friend or something. Oops. And they're not doing this. This is just some model that's all wrong. And yeah, so this is the idea. So you have some sort of model like this. You don't know really what's going on. I probably here, rather than relabeling all the red things, let's just say wandering is brown. That'll be easier for us. Okay, so let's say this is the kind of the picture that we have, and we kind of wonder whether or not these dots make any sense. And so then let's say they take the data, the position data, and they produce a plot. Right, so let's say this is time, and we'll work in the discrete time. So I'm going to line this up with one of the graph paper lines. And let's say this vertical axis here, this is like speed, where the distance divided by the number of steps or something like that, or the distance divided by the amount of time passing between them. And so, you could use this data set over here to construct some sort of speed as the person moved along. So, if they were If they were here at one moment and then here at the very next moment, they're moving quickly. If they were, here at one moment and then here at the very next moment, they didn't really move that much. So that's a slow speed and so on. So maybe the data looks something like this. So let's make it all, yeah. So let's say the data looks something like this. So at this time, slow speed. Maybe that's, oops, I gotta stick with the lines here. Discrete time, right? So something like this. But the speed is continuous. And then later, the next moment, they're somewhere up here. Then later, the next moment, they're like over here in the middle. And then down here, speed plummeting. And then speed rocketing away. Oops, they skipped a spot there. Right, and so you have this kind of collection of data and say, okay, oh, maybe these guys are all shopping, which was what was that, green? Dark green, yeah. And maybe these guys up here, these are all just wandering. And maybe you're the shop manager and you want to somehow figure out how to design your shop better, or at least just understand your customer behavior or something like that. And so you have this continuous, so here X, oops. So this is just speed, right? So it's distance divided by time. So this is a continuous thing. So we'll say speed at time t. Right, and so this is your sort of data set, and you want to try to use a hidden Markov model. Like, does it make sense that the speed, as you watch the customer kind of wander about in this store, does it make sense that the speed that they're walking would somehow be linked with whether or not they're consuming? Like, what does it even mean, consuming? Does it mean putting something actively in their cart or in their bag, or does it mean something else? I don't know. And so it seems reasonable that the speed would maybe somehow be linked to that. It might not be so easy to measure consuming, though. Like, for example, maybe there's a third state called stealing, a different color. I won't put it on here. Certainly, lots of examples have many more than two states in the hidden Markov model. And so I have to add in all kinds of colors for this and try to make a model. And does it make sense that the hidden thing here, stealing, consuming, or wandering, would those be a Markov process? Does that seem reasonable, that the probability that you're stealing at some moment is mainly dependent or mainly best predicted by whether or not you were stealing the moment before? That seems reasonable. And so on. So this is just an example of a kind of a continuous model. In your notes, you'll see a couple of other ones, animal movements, I think, and something to do with stock market behavior and like the sentiment of the of traders and so on. But yeah, so these are just sort of some sketched examples for how you can kind of imagine scenarios where a hidden Markov model might be useful, and we'll look at the details of that as we go forward. Okay, I hope you enjoyed that. I hope that you now feel like you know enough about queuing systems to maybe explore them a little bit on your own and maybe kind of prove some of the things that we skipped over. And I hope that you're looking forward to spending more time with hidden Markov models, our last topic of the class. We're going to cover that for the next and final 2 lectures of the class. Okay, I'll see you next time.